want to erase this, you should use alcohol, right? कैसे जाता है ये? How is this working? Alcohol.
Allowed नहीं है भाई. Allowed नहीं है.
Allowed नहीं है. So, okay. So let's look at this. Ecolipits neuron. So basically the model is pretty simple. What he says is, someone tell me.
Input a binary value and it will predict either yes or no.
Some input comes, something happens here, and some output comes, right? Input, some output. This is the most basic structure that these two people have defined. So, in their definition, the inputs and outputs are binary, right? They are binary, 1 or 0, 1 or 0, 1 or 0. So there are two functions defined here, right? One is f and the other one is g. I guess g comes first or f comes first? G comes first, right? It's their definition. We are going with their definition. So they defined g of all the inputs, I star input for all the inputs, as summation of all the inputs. They just fancy thing. All they do is just add all the inputs, right? This is g of x sigma xi, summing all the inputs. Say this is x1, x2, x3. So my g of x for this neuron would be x1 plus x2 plus x3, right? Here. So now they have defined another function called f, whose input is g of x. That is whatever value that you get after summing them is input to the function f. And the definition of function f is for g of x, if it's greater than or equal to some threshold value theta that we define, so that is f of g of x. G of x is nothing but whatever summed value is being input here, right? Summation is greater than or equal to theta. My output is 1. We are giving output as 1. If it is less than that theta, whatever the theta we define it as, it is 0. This is a definition. Simple. So it's like our basic neuron, right? What happens in the neuron? Whenever it basically works on the electrical signals, right? Whenever a pulse comes and it is more than the threshold value, it fires to the next dendrite. So that's what happens. So this is that model. So we have looked at a case where a person wants to watch a football match or not, right? So say, for example, you want to use this neuron model in order to model a function where a person will give some inputs and he wants to find out the function whether he wants to watch the match or not, right? So there are two kinds of inputs, right? What were they?
Inhibitory and
Inhibitory and
excitatory.
excitatory. Inhibitory is the one which is active, will inhibit the action of the whole neuron. That's the definition of inhibitory. And excitatory is where? What is excitatory? It's just like any other input, right? It's 0 or 1, it becomes 1. So it is high when it is 1, it is low when it is 0, or vice versa, as you define. Say x1, x2, x3 are his inputs, and x4 also. Right? So x1 is whether it's a match between Real Madrid and Barcelona, right? El Clasico, right? x2 is, what is x2? Some example.
Some other
variable that he wants to look at. Say it's a friendly match or not. Friendly match or not. One more.
Say is pizza available or not?
Is pizza available or not? Now we are talking. And say the last one, let's take inhibitory. If he is present at his home or not, right? घर पे है कि नहीं? Say he is outside doing some other work. This is inhibitory, right? If it is 1, that is he is present at home, he can watch. If it is not present at home, क्या कर सकते हैं? नहीं देख सकते हैं. So this is inhibitory in nature. This is excitatory, and this is excitatory in nature. So this guy's function, G comes first, right? G is summation of this plus this plus this plus this. Let's keep this aside for some time. We'll look at the math of how it works later. We have discussed last class. We can look at it. But let's see of these three, right? Say if even 2 of the conditions are met, any 2 of the conditions are met, this guy is happy to watch this. Say this is a El Clasico match and he has pizza available, he'll watch it. So how will we define theta there?
Greater than equal to 2.
They are greater than or equal to 2, right? Straightforward. Greater than or equal to 2 or less than 2. So even if this and this or this and this or this and this are met, it will always meet greater than or equal to 2. If all the 3 are met also, it is greater than or equal to 2, which means that he'll watch. Else he won't watch. Simple, straightforward, right? And how do you process this? So basically whenever this is active, you have one more. So this F's definition will be expanded in such a way that whenever this is active, it will go to 0. So it's like or and, right? You can see the simple explanation. So there we saw one more example of how to use this in order to construct an AND gate, right? And someone who did not attend the last session, tell me how can we maybe make a AND gate, right? There is x1 input, 2 inputs, 1 output. Now the functions f and g. Can play around with theta in order to make it an AND gate. कैसे कर सकते हैं? Someone try. Who did not attempt the last time?
Parallel bucket.
Huh?
What kind of?
So basically you are getting x1 and x2. These are binary, right? What is an AND gate? Both and
दोनों true हो जाएंगे.
दो true है तो we get a true outside. So how can we define an AND gate using this?
So f greater than theta should be greater than equal to 2.
Theta should be 2, right?
Or 2, yeah.
So your f of g of x should be greater than or equal to theta, तो 1 आएगा. F of g of x less than theta तो 0 आएगा. So I am defining theta to be 2. Let's say 2, right? So when I get 1 and 1 as inputs, 1 plus 1 is 2. That is g of x is 2. F of g of x is 2, right? So that 2 is greater than, this is g of x. So g of x, that is 2, is greater than or equal to theta, which is true, right? So my function f will output 1. So 1 will be the output. Say one of them is 0. Is it greater, this 0 plus 1 is 1, which is less than 2, which means this condition is met. So it is 0. 1 and 0, the same thing. Exchange करने पे, right? Symmetry. 0 and 0, done. Right? Can I have any other value apart from 2? Anything apart from 2? Can we have 1.5?
But input is only 0 and 1, right?
Input is 0 and 1. My theta is a value that I can decide, right? So it need not be an integer only, right? Even if I put 1.5, will it be true? काम करेगा ना? 1.5.
काम करेगा.
Right? So any value between 1.1 plus, right? 1 plus any value. So open one, sorry, yeah, we can use this. Open one to closed 2. Beyond 2, it doesn't go. Open 1 to closed 2 is a solution to this, right?
Right.
Not to make it an AND gate, which means that there is no one particular solution. That's the best part of this machine learning. So we know that 2, if only integers are there, then 2 is the only answer. But if you can leverage on the fact that instead of 2 I have other values also, 1 और 2 के बीच में जो भी values है मुझे solution देंगे. So that's what these neural networks are so good at, because you don't need to get the exact solution. You can get into any of one of these solutions in order to give you the perfect answer. So that's why approximating way these are far better. But there is a problem with this. This is only binary, right? And I don't have any weightage to any of the inputs. So then comes the next model, the next iteration of this. So we have looked at how to make a AND function, similarly OR function. OR function also you guys can look at. Inhibitory and not OR. Okay. We get into the what is the physical interpretation of that? It is actually a straight line. The point is falling here or within the line. If it is falling within the line, it will make it 0. Beyond the line, it is making. So it's basically getting a boundary. Just like how theta is a unidimensional boundary, you can play around with multiple thetas for a bidimensional or a multidimensional boundaries. That's all that. See, if you are going for 3 dimensions, you are making a plane which is going like this. Anything which is on this side of the plane, it will predict as 1. The other side, it will predict as 0. So the guys, Macaulay Templet, these guys have said that, okay, we have found the God particle. We can solve everything in the world. But sadly, there are other people who are continuously questioning the peers in the scientific group. So in academia, that's the thing, right? If you say something is achieved, there are other people who wants to say that maybe not. So they have found out, there was a book which was written where the whole book is about disproving that this can't be used for approximating any function. You can't generalize every function using this. But then came another guy who came up with perceptron. Right? So let's look at what this is. We won't go so deep into this also. And after this we'll give you a introduction of what backpropagation is. Then we'll get into hands-on coding. Every time I say this, we'll get into hands-on coding in the next session, but this is the session we'll be getting into. Cool. So it's the same, right? x1, x2, x3, some xn. What are these? W1, W2, 3 and W1. So that is going into this. And have a summation operator sigma. Then whatever output is coming, he calls it C. And another, what is this? Sigma.
Sigma.
This and this both are sigma, right?
Epsilon means sorry.
This is also sigma.
Both are sigma.
Yeah, both are sigma.
अलग-अलग language.
Exactly. So whatever is coming it as out as, he calls it A, output. So what exactly are we doing here? Earlier x1, x2, x3, x4, so on xn, they were only binary values, right? Now they have slacked it a little bit and said that they can have values anything between 0 and 1, right? 0 and 1. W1, 2, 3 and these things are weights. Earlier we had unitary weights, equal weightage for everything, right? Because earlier when we were defining, this wasn't there, which means that it was 1. x1 into 1 plus x2 into 1 plus x3 into 1, which was x1 plus x2 plus x3, so on. But here, now we can define weights, individual weights. So we know, say an input has more weightage over the other one, you can adjust them. This is the same operator, right? Summing all the inputs coming after multiplying them with the weights. After that comes, I have an activation function. The function that I have written earlier, right? G. G or F? Huh?
G is the one that sums.
G is the one that sums. That is this. So this was F. Exactly. So F was the activation function. In the previous example, F is the activation function. Why is it called activation function? Because it is the one which is helping the neuron to activate or not to activate, to fire or not. So if you look at the mathematical representation of it, in a vectorial form, right? This will be the output. Prediction y dash will be wx plus b. If greater than or equal to 0, this will fire. Wx plus b less than 0, it won't fire. Good. So yeah, we'll get into that. So far we have seen that there are inputs that are coming, right? So there is a problem with this one. What is the problem? All these can go to zeros. When all of these go to 0, which means that in one of the possibilities, all of them, when they are 0, the whole thing is 0. If I don't have b, it is y is equal to wx. If you see it in a single dimension, although these are vectors right now, vectors are nothing but multidimensional numbers, matrices. But let's see in one dimension. Y is equal to wx plus b. What does it represent?
Straight line.
It's a straight line. In 2 dimensions, it's a straight line. So, if I don't have something called b, y is equal to wx. What does it represent?
This origin.
It's a straight line passing through the origin, right? So, in the origin, I have all these straight lines, all infinite possible straight lines, but all passing through the origin, right? But what if I have a function which can translate also? How am I translating it? By changing the value of y-intercept, right? B is the y-intercept. Yeah. So when I change the value of b, earlier it was always 0. Instead of 0, if I have 1 or 2 or 3, it can translate. So it can generalize better. That is, so they named that b as bias, right? It's a bias which doesn't have any correlation with the inputs that is coming. It is independent of the inputs. So that b is that bias term. We can go even more deep into the mathematics of why bias is needed and all that, but I don't think it should be out of scope right now. If someone is interested, we can get into that later. But you guys get the general idea, right? Why B is being used? To generalize it better. It is independent of the inputs that are coming. It is dependent in a way, in a holistic sense, because that B is figured out based on the inputs coming, but they don't have a one-to-one relation from the inputs. So yeah, that B is being added directly.
Can there be multiple biases?
Huh. Nice question. You tell me. Can it be? Everyone can try. So in what context are you asking? No. If you are saying can there be multiple biases, what do you mean by that?
Maybe one related with inputs in some ways. So,
Okay. So let us see. Everyone can try answering this question. Can there be multiple biases? That depends on the question, right? The question frame is right now open-ended. Can there be multiple biases to just this one perceptron? Yes or no? For one perceptron, there can be multiple biases. But at the end of the day, they all will sum into a single number. So at the end of the day, you are having only one bias for a single perceptron. No matter if I give B1 and I give another B2, what am I doing? W1x1 plus W2x2, so on, plus B1 plus B2. But B1 plus B2 is some other B. So for a single perceptron, it's a single bias. It's always just one bias. But for multiple perceptrons, I'll have different biases, right? So when I put this in tandem, so say this whole perceptron, I note it like this. Some inputs are coming, some outputs are coming. I have another perceptron here. Maybe as outputs are coming, I can connect them like this. So they have their own B. So this B is, say this perceptron is I1, this is 2, and this is 3. So this is B1, B2, and B3. So each individual perceptron will have its own bias, which is different from the other. And at the end of the day, they will have only one bias. So you guys remember SGD, right? SGD? Gradient descent? Right? Gradient descent algorithm. Yeah, then? Or do we have to go through it once? Just you guys remember, right? Rubel was explaining how linear regression was, how did we solve linear regression problem without directly posing the equations. Good. So now we know this, right? So even, let's take an example of, so this is the general thing that we do. In linear regression, what did we do? We posed a hypothesis. What was the hypothesis? I was hypothesizing that this might be the solution. A straight line, I have fixed that, and I have given a mathematical equation that, okay, this is the straight line that it will be fitting in, theta 1 into x plus theta 2. Right? Then I initialize that theta 1 and theta 2 with some weights. That theta 1 or theta 2 का कुछ value मैंने दिया है, some random values. So that is what is initializing weight values and biases. Theta naught was the bias in that case, theta 1 was one of the weights. Both are weights basically, but that particular weight is called bias. It's a special name given. So now what you do? You do a forward propagation. What is forward propagation? So input अंदर जा रहा है, black box model है, we have an output. So when input goes, output comes. This is the forward path, right? In order to get to the solution, the predicted value. That is called as forward pass or forward propagation. So what you do? You put some values, you have some weights and all those things that are already defined initially. You have initialized with those weights and biases. You have given some input and you are expecting an output. You get an output. This is the predicted value, right? But from your data, you have the same inputs, but there is an output that is already there, which is the real output, the absolute real output. So this is the predicted one, that is the real output. The whole idea is to change these weights and biases in such a way that whenever this input is given, I meet the real output, so that this function is generalizing to that particular data set. So if I give a new input which it has never seen, it will give an output which would have been true, because that's a probability again. So you forward propagate. You check the error. How do you check the error? You got a forward propagation, you got a prediction minus real. That is your error. How much is it lagging behind or forward than that of your. Then you check the error. You back propagate and adjust weights and bias. Right? You just back propagate and adjust the weights and bias. Yes or no? Yes. But how do we back propagate is the question. Right? This is where a lot of people are like, this is very hard. We don't understand how this is happening and all that. Today we have a very simple example where we deal with a little bit of math and we'll understand what backpropagation is. Everybody talks about backpropagation in machine learning. I guess I can say strictly that maybe 2 or 3% of the people who are doing machine learning know how backpropagation works. Definitely. I have talked to a lot of people that are working on machine learning. They have no idea. They know that backpropagation works, weights are adjusted, some magic is happening, but they don't know what exactly backpropagation is. So let's look at that today, how backpropagation happens and how weights and biases are adjusted. So you guys have actually seen a precursor to the backpropagation. The other day when Rubel was discussing the SGD, what you guys were essentially doing were, you guys were finding out which direction to move, how much to move, and subtracting that value from the weight, right? And slowly you guys have come to the actual solution. You guys remember that? Gradient descent wala? So this is the optimal value where your prediction minus real across all the data set is the minimum, the least. But how are you doing this here in one dimension or in a simple example? You have to apply the same to a perceptron model also. Then repeat for all training examples. Repeat again and again and again and again, so that will learn the needed function. Let us see that example today. But before that, let's see an AND gate in the. You guys know what an AND gate is, right? Let's see how to do that in this. So, can you guys just try? Take a perceptron. Now you guys know the pseudo steps of how to do a forward pass and a back pass, right? Let's take a perceptron. Weight W1, x1, x2, output. You guys know, here summation happens, then it is passed to a activation function, right? They're only fancy names. They're nothing but simple functions that you guys have already seen. Nothing anything about it, right? And you get an output. With this example, can we try to construct a AND function? The most basic that I can make is initialize weight1 and weight2 to 1 and use this as the same function that we have used earlier. But that is cheating, right? That is you trying to replicate a MP neuron using a perceptron. But that's not the idea of this. Can you guys quickly try? You guys have paper or something? Or just intuitively also you can look at it. It's okay. You don't have paper or pen. Just think about it. It's good. Is there something that is missing in the diagram?
B.
So we can get three equations.
Uh-huh.
W1, so suppose we take x1 as 1, x2 as 1.
Mm-hmm.
So W1 plus W2 plus B equals to 1.
Equals 1, yeah.
Right? And then next equation we take x1 as 0 and x2 as 1.
True.
So it should give a result as 0. So that will be W1 plus B equals to 0.
Yes.
And then similarly W2 plus B equals to 0.
Mm.
And then
We have three equations, three unknowns, we can solve for it.
Yeah.
Awesome. That's exactly what I wanted. I wanted someone to answer that. Right? So we have three unknowns, three equations. Can we solve the problem? Yeah? Three unknowns, three equations. We can always solve the problem. Nice. If we put x3, then how many unknowns will be there and how many knowns will be there? Will the number of equations increase? Cool. It's okay. At the end of the day, you can solve that problem also using the same method. But this is us trying to solve the equations directly. Say we don't have that procedure, right? Because all problems which are posed don't have ample number of ample number of data points, right? Or even though they have an ample number of data points, we don't have a way in which we can figure out these, because this is one neuron. Now I'll have multiple neurons in tandem. So the number of equations that are generated would be way too high, right? So that kind of solution will be harder for us to get to, because the kind of dimensions that we will be solving tomorrow will not only be in squares. So finding inverse and all that will become a problem. There are something called pseudo inverses which we can find, but they are also approximate solutions. So that is one way of solving the problem. Equation कुछ मिला, x1 plus x2 is equal to 3, x1 minus x2 is equal to 5. Sum both of them I get 2x1 equals 8, right? x1 equals 4, which means x2 is minus 1. I can do this. What else can I do? x1 plus x2 is equal to 3, x1 minus x2 equals 5. Most simplest thing, if you don't know how to solve this, is brute force. You take x is equal to 1, x1 is equal to 1, then see whether x2 का लिए solve होगा, you're getting a unique value or not, and all that. That is one of the other ways of solving it. So basically this is trying to do the same thing, but in a more smarter way, by looking at how to move towards this value, where is my mean and how can I move towards it faster, right? That's what we are trying to look at. So let's see. say w1 x1 plus w2 x2 plus b is the y, right? In this, w1 x1 w2 x2 plus b is the output. Is that the direct output? No, because we have an activation function in the middle. But let's remove the activation function for now. Let's think that activation function is not there. So x1, what he is saying is, let's take w1, w2 as 1 and b as some minus 1. Just like what we said. We get, passing the first row, the AND logic table, x1 equals 0, x2 equals 0, 0, 0, minus 1, minus 1. So from the perceptron rule, this is equal to 0. Right? 1, 1, it is giving you a 0. So if we have the function as inverse, 1, 1, 0 ayato, we can make it as 1. So for that reason, this row is correct and we need not do any backpropagation. So what exactly is happening is, why do we have to do backpropagation instead of solving the function, solving it directly when it is possible? The thing is, there are some limitations. Say for example, you have limited RAM, right? You always have limited RAM. Your computational power is also limited based on the RAM of your GPUs and CPUs. So what happens in the long run is, you can't show all the images at once. Sorry, not just images, any data. You can't show the model, all the data at once. So at any point of time, you will be showing only chunks of data in batches. So what happens then? That's the thing, right? When you can show all of these data points at once, you can get n number of equations, n number of unknowns, you can get solutions, n solutions. This is mathematically possible. But when you are limited by this, that's when stuff like this will help you out. Because at the end of the day, you have to find out the solution. You don't have the computational ability. So what people have come up with is, they have broken down it into multiple batches and seen, if I show a single batch, is there a possibility I can get to the solution? Right? Say for example, you are looking at images. Say at one time I can load only 10 images. But the whole function that I am trying to build has to look at 10,000 images. What can we do? 10,000 images can't be loaded in the RAM at one point of time. So we use this kind of algorithm where 10 images are seen once, it gets to a little bit better solution. Then another 10, another 10, another 10. Then we shuffle all the 10,000 images, make 10 of batches again. That's the reason we are doing all this, right? So if only at one point of time, here he is saying that I can show only one example. एक example बता पाऊंगा. So in the truth table I have how many? In the truth table I have 1, 2, 3, 4. 4 data points, right? XY and the output, XY output, XY output, XY output. So he is saying, in my RAM I can only load one example at a time. If I am feeding only one example at a time to my model, how can I solve this problem? So he says, as you have seen earlier, initialize weight values and bias and forward propagate. He initialized it to W1 as 1, W2 as 1 and B as minus 1. Done. He has initialized the values. Now he is forward propagating with only one example. So one example, x1 into 1 plus x2 into 1 minus 1. x1 was say 0, 0. What did he take in the example?
0, 0.
Sorry?
0,
0, 0. Okay, he took 0 and 0. So 0 into 1 plus 0 into 1 minus 1, which is minus 1, is less than 0. So y dash equals 0, the output. Therefore this row is correct, right? It is already following the required conditions. Now he goes to row 2. So this is the second example I am giving. I have cleared my RAM, I have removed the first example, I have given the second example. Now from the perceptron rule, with the same W and B's haven't changed yet, right? So now if I take x1 is 0, x2 is 1, in the AND gate I will get a 0. So 0 into 1 plus 1 into 1 minus 1 equals 0. So from the perceptron rule, if Wx plus B is greater than or equal to 0, y dash equals 1. So this row is incorrect, right? It had to output what? You guys following? Should I write it on the board? Yes, I write it on the board. It will be more easy. W1 x1 plus W2 x2 plus B. This is nothing but this is the y dash predicted greater than or equal to 0, 1, less than 0, 0. First step, initialize the weights. and biases. I am taking weight 1 and weight 2 as 1. I am taking biases minus 1. Any random value I can take. This was his choice, just we are following that example. That's it. So now, in the first row, I know 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. Sorry, yeah. And 1. So B equals minus 1. So in my first one, W1 into X1. W1 was 1 into X1 was 0. Plus 1 into 0 equals
Minus 1.
minus 1 equals minus 1. So it was less than 0. Hence my output y dash is 0. This is correct, which means that I need not change my weights and biases. The second row was actually 0 and 1. 0 and 1. So weights did not change. So 1, 0, plus weight was 1 into 1 minus 1 is equal to this
0.
0, which is greater than or equal to 0, right? Hence my output is 1. But actually my output should have been a 0, right? These are not matching, which means I have to do some correction to the weights and biases. So what he is saying is, so you want the values that will make the combination of x1 equals 0 and x2 equal to 1 to give a y dash a value of 0. So if we change b to minus 1.5, what will happen? So how he is getting to minus 1.5 and all is based on his intuition, which is his brain is already solving. But we will see how that happens in a couple of minutes. So he is saying if we change the b to minus 1.5, so now earlier my w1 was 1, w2 was 1, b was minus 1. Now I am saying I'll change it to b to minus 1.5. So what will happen here? So back propagate. Now we have back propagated, some bias changed. So weight into 0 plus 1 into 1 minus 1.5. So this output is minus 0.5, which is less than 0. It gives 0. Right? Now this is okay. But what is the problem in solving this kind of a problem? Now that I have catered to this example, we should also check whether that is catering to this example. Because tomorrow, this is my final W1, W2 and B. So I want to see whether this is also solving this one. So let us quickly look at this. 0 into 1 plus 0 into 1 minus 1.5. So it will be total minus 1.5, which is less than. So my output will be correct. So it is solving both of them. Now let's go to third. What do you do in third?
1, 0, 0.
What do you do?
That's the same.
That's the same thing, right? It's just symmetric. So flip करेंगे तो change हो गया. So we need not change any of the weights and biases. So carry on to the next row. In my next row I get 1, 1 and this. So if I do 1, 1 and that, the fourth one. Now my final weights are 1 into 1 plus 1 into 1 minus 1.5. 1 plus 1 is 2 minus 1.5 is 0.5, which is greater than or equal to 0. So my output will be, which is the required one. Hence solved. So here he said, let's take minus 1.5. Even if I take minus 1.4, the problem would be solved. So how he took minus 1.5 is very intuitive for us humans, because we are just tinkering it around. In our brain we are trying to figure it out. But how we are actually going to solve it in backpropagation is what we'll look. So similarly there are examples of how he has solved OR gate, NOT gate and all those. You guys can go through it. XNOR, they are very interesting. See, now you can see multiple inputs are coming, right? This AND gate was the AND gate that you guys have already solved just now. This NOR gate is something that you would have solved if you have gone through that. Now those two have become two inputs on their own, and this is some other input which is coming to it with an OR and another bias. You asked, right? There can be biases. So this B and this B are not same. This is some B1, this is some B2. See right now here, but these values are always ones. So what they are doing right now is, by putting these equal to 1, they are just changing the weights of them. So instead of putting b equals minus 1.5 here and b equals minus 1 somewhere, I am putting b equals 1, b equals 1 and changing its weights. It's the same, right? I can say a into like 1 into 2 or 2 into 1. It's the same. I'll be adding 2 only. So that's the convention that they are doing. So yeah, you can see that multiple gates are now being used in order to solve a bigger problem, an XNOR, stuff like that. So pretty interesting. So I guess, yeah, let's look at the backpropagation. Right. So you guys have followed till here, right? No doubts, nothing.
सही पेन एंड पेपर चाहिए क्या?
इसके लिए नहीं not. I'll just explain. I'll show you guys the example how it is done on the comp. I guess that will be done. Yeah, it's better you guys take it like for 5 minutes. Do that. If you guys can get pen and paper, it would be good because you guys can also do and see for yourself.
हो गया और अभी ये लोकेशन ट्रैक कर रहा है अब किसे
येलो मतलब
अब फिर बस हम तीनों ने ही खोला है सब हम लोग ऑनलाइन दिखा
उसमें लोकेशन कैसे ला जाए
तो जीपीएस
लोकेशन कैसे पता चलेगा ऑफिस में खुले
ऑफिस में हो या बाहर हो।
as long as I'm ये क्या है
GPS के बिना
ये
हम ट्रैक कर लेंगे अभी कहाँ पे।
अरे ये
इसके बिना कैसे
चल
ये
हम्म,
डेडली और
GPS के बिना GPS ऑफ
unsplash unsplash
अभी हम ट्रैक कर लेंगे कहाँ पे हो।
मेल आईडी खुला है
वर्क फ्रॉम होम बोल के और जाते हो ट्रैक कर लेंगे।
तो ये तो बताएगा कि घर पे है कि नहीं।
unsplash
हाँ लैटिट्यूड लॉन्गिट्यूड पता
फिर
चलेगा।
सही नो
नहीं कुछ नहीं है।
मॉल में कॉल मिला में अगर तुम कॉल मांगने में तो एक पुश नोटिफिकेशन आएगा गो टू ऑफिस काम नहीं है क्या काम करो। फिर एक और मैसेज आएगा
तो मॉर्निंग वॉक पर
ये एक्टिविटी इसके पीछे कर
काम करो ठीक है। हम कोई क्या करेंगे कुछ जगह लगी से
you know that you can drive a car, right?
बट फिर इन सब
Just
जगह हम
the
डाल देंगे। इनमें से एक जगह हुआ तो
यानी कि वहाँ जाकर जीरो जाएगा।
अब जीरो टू डाल देंगे।
Related.
What will you do in the end is drive a car.
How do I make it
It's
faster?
going on engine.
Say, what's the
So अभी दिखाएंगे। ये क्या ब्रेक टाइम आएगा?
So if I make
रिकॉर्ड अभी भी
कुछ बोल रहा है
yeah, what is this? Reset itself is at 5.
एडिट कर लो इसको क्लिक कर।
Nice. Hmm? I know.
So now, irrespective of time, you can get your 8 hours sleep. Avoid sleeping, just put 8 hours on it.
Okay. Guys. Ready? Okay, now you guys have got a simple idea of what a perceptron is, right? Input, output, input, output. Let us see a very minuscule example. Like it's like the tip of the iceberg example, but you will get an intuitive idea of what exactly is happening in the back end. When I show you the coded example, you guys will know what exactly is happening, irrespective of whether it is a complex example or a simple one. So let me take I1, this is I2, this is H1, this is O1, right? Got it? For simplicity's sake, I am neglecting bias, right? But if you add bias, it will be the same with extra inputs, right? Cool. So I1 is nothing but my input. I'll just define it as 0.05. Example that I taken. This input I2 is 0.10. So this will have some weight W1. I'll name it weight W2, right? This H1, then it goes, you have weight W3, and output. I am defining my output to be 0.9. Take 9 because all the math is already on 9. So, so this, you guys got it, right? This is just input. There is nothing. This is a simple perceptron with nothing but no activation function, nothing. Whatever is coming, it is just sending out. You can take it as that. This is also just like that. It is, if 0.1 is coming in, it will send 0.1 out of it. But how it is getting to the next one is depending on the weight for this one. So this is the actual perceptron that we have seen, like full-fledged perceptron without the bias right now. This is the full-fledged perceptron. It has weights, it has inputs coming in from some other perceptrons or modules, whatever, right? This is another perceptron. It is a single input, single output system. This is used for output. So I call this I1 and I2 because this is the input perceptrons. This is the hidden perceptron, because for someone like if it is a black box, you can only see what is going in and what is coming out, right? So this is hidden, and this is the output. Naming convention clear, right? Hidden, output, input. Cool. So this is how I define. And for this example, to keep it like for brevity's sake, I am taking 0.05, sorry, 0.05, 0.10 and output as 0.99. That's it. I'm not giving it multiple inputs as in multiple examples. I can generalize my perceptron for multiple data points, right? But here the data point is only one. Input is some p comma q, which is 0.05 comma 0.10, and my output should be 0.99. So my idea is figure out these weights W1, W2 and W3 in such a way that whenever I give input as 0.05 and 0.10, my output should be 0.99. I can do it in multiple ways. If we humans try to figure it out, I can say multiply it with say 0.05 into 1 and this 0.10 into some W, and here just put the weight as 1 and I send the output to 0.99. I can find out some value for W, right? Say if I give 0 here, this would be 99. W2 would be 99 if I don't have any
Hidden
range.
trial basically.
If I do, right? If I as a human can do. Or I can split it. 0.1 into, instead of 99, let me say I give 6, 0.6. 0.1 hai, I multiply it with 5, so it will become 0.5 plus 0.05 I multiply it with 2. So it will give 0.1, sum them 0.6, put the weight W3 as 1. So there are multiple solutions possible. Why? It's because you are only taking one example. If there are multiple examples, then your W1, W2, W3 will be a little difficult to generalize to. So let us see how backpropagation helps us in order to find out W1, W2, W3 for just one single example. So here my whole idea is to make a function wherein the input is this, will output this. Right? That's it. We can have multiple data points, like it could be, say I have say house price. What was the example that we were discussing the other time? House price, right? So this is house. This is my quality of house, say, or house price in lakhs, and this input is my some metric. This output, this another input is another metric. So I am giving two metrics, and I am estimating my house price. So I have multiple houses, right? You have a house, I have a house, he has a house. So I take multiple of those values. I have these metrics defined, and I have the price of your house, someone else's metrics, someone else's house's price, and this. Then these W1, W2, W3 will be sorted based on all these examples. I will use all these examples in order to use this. Maybe this might not be able to generalize, then I will increase the size of it. The inputs will be more. This hidden layer ke andar jo bhi perceptrons hai, that will be more. Instead of having only one hidden layer, I might have multiple hidden layers like H1, 2, 3, 4, 5, H11, H12, H13, H14, and multiple hidden layers. Outputs could be only one, or I can have multiple outputs. Say I am outputting price of something, price of the land, comma, I am outputting, say what else?
Registration cost.
Registration cost, yeah, anything, right? So I can have multiple outputs. So it is a architectural problem that we can solve. So it is up to you whether this architecture is enough for me to solve this problem. As I know, this is a very simple problem where I am only inputting two points and getting a single point. I am using the simple architecture. I can go pretty complex, and people have gone crazy on this. We'll look at some really crazy architectures in the coming lectures, but yeah. So you guys got the gist of what we are trying to do? Simple example, right? Inputs are just two, one output. We want to find out W1, W2, W3, not by direct propagation, but from back propagation, right? Not directly solving it. Cool. So here, damn, this board will be so small. Right?
You can reduce the size of the flag.
Huh? Yeah. But I want
on the
everyone to see that.
Oh, you can reduce the size there.
Write it on the corner somewhere.
You can use the tab.
Hmm?
Zoom in the mouse.
Tabs, right?
Abhishek.
iPad. Abhishek has it.
What was that? How will you show?
We figure out a solution.
You got it. Abhishek just went out.
Went?
लेके जाता है क्या? Just went out. Nobody was there.
Good there. What was it? 320.
Sunil password क्या है?
881320.
811.
812.
Show some Sunil side से.
8 बार कुछ बताना है क्या?
दिखा सकते हैं. कीबोर्ड का कलर है क्या? मैजेंटा. सुप्रीता को पता है. What is X code? उसको पता है, याद है, बोल रही है. /B//B/UT2/YWT5/RR/.
F11 is the
Probably have to put one down. That's okay.
fancy stuff. कैसे करते हैं इसको? Mail required. Who uses this?
Just tip से उठा.
ऑन करने के बाद हो गई.
Oh, इससे मैंने इसका. Give me 2 seconds. I just figure out. Oh, amazing.
You can undo.
Yeah. No board from this. Yeah, it's working. Cool. So you guys, okay, I'll just keep it here, and everything else I'll do that, right? So, huh? I can sit closer. Thank you. So let's look at. So initially, what do? We randomly initialize the weights, right? That is the step. You guys remember the steps, right? Randomly initialize the weights. So in my example, I have initialized it to 0.1, 0.1. Probability also? Yeah. I was lazy. Wanted to initialize everything to the same. So there are multiple ways on how to initialize the weights also, but it's cool. Right now, 0.1, 0.1, 0.1. And yeah, that's it. So initially, when I give my example in, what will happen? What would I get? So H1, what is the input for H1? So H1 has an input, right? input coming in and an output going out of it. So what will be my H1's input? This weight 1 into input 1, that is 0.1 into 0.05 plus weight 2 into
0.1 into
0.1 will be my input for H1. That value is 0.01. Sorry, become rusty on my. Yes. So that will be the input for my hidden layer ka just one unit that I have, H1. Now what will be my output from H1?
into 0.1.
Into 0.1 output will be, so this is g of,
This into 0.1.
this is just g of theta, right? This is just g of theta. I have an activation function,
Okay.
right? Okay. Let's discuss about one special kind of activation. There are multiple kinds of activation, but I want to discuss about a single activation function today. We'll discuss about the other activation functions later. Let's take, there is something called a ReLU, right? Not value, ReLU. It is rectified linear unit. Some fancy name. कुछ नहीं है, simple है. Its graph is like this. I have a red one. Deception. Or inception. Nice. Both. So it's defined like this. So why is it? It's a linear unit. It's straightforward. It has just two linear. It's a linear curve, right? It has an inflection point at 0. It is rectified because instead of having a single linear line, I am having two lines which are intermixed, right? So what does this guy do? If I have a value less than 0, it is always plummeted to 0. And if I have a value positive, it will give out that value. That's it. कुछ नहीं करेगा. He is a guy who is sitting there, looking here into the input. Positive है, भेजो. Negative है, मत भेजो. ऐसा अपना गेट के पास होना चाहिए. Victor Labs का. You got it? Right? Anyways, so output is that. So here in that output, my output would be simply 0.015. क्यों?
Greater than 0.
Greater than 0 है तो उसे भेजो, नहीं है मत भेजो. That's it, simple. So my now output O1 will also have this O1, the output wala layer, has an input and an output, right? Following? Any confusion, please tell me, because I can't explain it again and again. I can, I will, but it's better you guys concentrate now because confusion kuch nahi rahega. So input, output. So for this, the input would be the output of H1 multiplied with its weight. This weight here is 0.1. The output of this guy after the rectified linear unit has sent him is 0.015 into 0.1. That would be my input to this. That is 0.0015. So my input coming is 0.0015. Awesome, right? So Abhi, what happens here in the output? If I have a rectified linear unit here also, same output will go, right? Straightforward. Nice. So it will go 0.0015. This is the total output, right? Total output of my whole model. But when I give this, what was I expecting? What I wanted? 0.99. But kya hai? 0.0015. Which means that predicted and the absolute real value is not matching. Which means I have an scope of improvement because there is some error. So what is my error? Error equals?
0.99 minus 0.015.
Yes, that is one way I can quantify error. But what is the most used way that we have calculated error? Squared error, right? You know why also. I need not go through it again, right? Squared error क्यों use करते over absolute error or normal error? Right. So half of y predicted minus y true whole square. That is error equals half of y predicted was I can write it y pred minus this or this minus this, right? I can do that because it's a square. I can write whatever I want. This error will come out to be something around 0.4885. Okay? Cool. Doesn't matter. Math will just work out. You just have to understand the how it is done. Okay. Now this page is going to be a little tricky, but yeah. Actually, I need not use that also. This is more comfortable. Old school. But now I guess I have to do that. Okay, right? So I'll just explain one simple unit here. The back propagation that happens only till this. Okay? You guys can interpolate and extrapolate it to other ones later. I'll just explain till this because if I go here, but time like that. It is just time consuming. That's the reason we are asking computers to do this as opposed to that of humans, right? Strictly speaking, if you look at the most simple example of MNIST, right? Just fun fact, it's called MNIST. In MNIST data set, we have 28.
What is this?
It's some full form. Okay. National Institute for Standards and something. I don't exactly remember. But these guys have given a data set. So these guys are someone who has set some standards. So these guys have given out a data set on numerical numbers. So you guys remember we used to write letters, snail mail. Letters लिखते थे ना एक we send letters, right?
इंग्लिश के एग्जाम में लिखते थे एक्चुअली कोई नहीं लिखता
Exactly. So those letters, sadly they are out. But yeah, previously there was a problem that was that people wanted to solve. They wanted computers to look at the pin code and sort it automatically. You know that people used to sit and look at the pin code and do that. Have you seen that? Most satisfying videos where people are doing just this, looking at it, right? Now they wanted computers to do it because there are a lot of mails that used to come. But that was the problem posed. So this was an image OpenCV problem that somebody had to solve. It was an open problem. And people have come up with various techniques in order to solve it, like ऐसे जो भी है, intuitively we have created minus 1.5 in the previous example. There were people who sat down and made matrices with values like minus 1.5, 0, 1.5, say, they have experimented with it, trial and error, and figured out some ways with a lot of error on how to say, अगर इधर 2 लिख के ऐसे, somebody, doctor होगा, 2 को ऐसे लिखा कुछ, right? How to say whether it's 2 or 3 or 1 or whatever, right? So somebody has sit down and solved it for this, but it was not generalizing for something like this, and stuff like that. So if you look at that problem, it is a 28 cross 28 image, right? So which means how many do we have? 28 cross 28, 28 and 28. Operator, इसको थोड़ा ऐसा shift करते हैं ये. 724.
700 क्या?
720? 728?
नहीं 4
88 से 64, 4 आना चाहिए.
724
724. Cool. 784, huh? 784. So that many number of, if I make it, that many number of inputs are there, which means 728 pixels, say they are black and white, 728 inputs are coming. Here only 2 inputs we are trying to solve and understand. 728 inputs are coming. And in order to solve a problem as complex as that, in my hidden layer I should have, say 10 perceptrons here. I have one more hidden layer, say I have some 4, one more hidden layer, one more, say this is the output layer. We know how many digits are there? 0 to 9. They are enough, right, in order to categorize all of them. So I have 10 outputs. So every time I give an image of 2, this is 0, this is 1, this is 2. This has to get highlighted, stuff like that. So the number of calculations. So here look at this. यहाँ पे अगर 10 है, यहाँ पे कुछ say यहाँ पे 20 है, यहाँ पे 10 है. How many combinations will happen? So each of this will send 20 outputs. For 20 of those. This will send 20. This will send 20. This will send 20. Number of weights?
2000.
Exactly. Right? How many combinations you can make? That many. 20 into 10 and again into 10. So 2000 weights are there. I haven't included my biases yet. Right? Let's remove the biases. So you can see how quickly this is becoming a complicated problem. Right? It becomes even complicated when we are dealing with colored images. So right now we'll just try to understand it for a single. बस एक weight को कैसे update करेंगे ये देखते हैं आज. We'll just look at how to update only single weight. Then you guys can, if you want, solve that MS problem with your bare hands. That will be your homework problem, right? This
For
assignment. Whoever does it, we'll meet you in the next life. Cool. So yeah. So at the end of the day, let's keep this aside. Let's look at simple math of what derivatives are, right? So say, okay, I have a plank here. I have another plank here, and I have one more plank here. So this plank is moving, okay? There is some kind of a dynamics happening between both of them. This plank is moving. If I pull that plank, say the dynamics is friction. There is some different kind of friction here and this here. Surfaces are different. There is a brick, there is a paper, there is something, say. Very bad example. Kuch aur likho. Please, take some other example. Frictions are different. There is F1, there is some F2 kind of friction. When I pull this guy will move, but a little bit, right? He will move based on some dynamics that happens between them. And this guy will also move because I am pulling him. This is also getting pulled. This is also getting pulled. This will also move a little based on the dynamics that they have between them, the static friction and the dynamic friction. So relatively, if I am pulling this guy will get pulled by say some X amount, and this guy is getting pulled by some Y amount. Next time when I pull this guy will pull this guy with some X plus delta X amount, this guy with Y plus delta Y amount. For a person who is outside, how much did this whole guy move is delta Y plus delta X from the previous position, right? So this is becoming relative, right? I know that movement of this guy with respect to this, say this is Z, dz by dx, right? And this is dx with dy. So if I have to find out the whole compounded relative movement, it will be like dz with dx plus dx with dy, something of this sort. So you guys understand how we are getting to chain rule of looking at derivatives. One thing is dependent on the other, that is dependent on the other. You derive this with respect to this and this with respect to this. That is chain rule, right? So you guys can see a pictorial representation of how that is. Although here it is additive, there it becomes multiplicative, right? Additive is multiplicative, right? If I am adding, if I am adding one apple 10 times, what exactly am I doing? Multiplying that one apple with 10. So additive is multiplicative, which is subtractive and also divisive. Right? Cool. Nice. So now let's look at how to change W3. That is our whole concept, which is, so I call this error which is coming out as E0. Cool. Error, half into y prime minus y2 square. So my whole ultimate goal is to find out change of E0 with respect to my weight 3. How much if I am changing my weight, my E0 is changing, right? Say if I am changing my weight by 3 units, finally if I am getting something like 2 by 3, 1 by 2, easy, 1 by 2. So if I am changing my W2 or W3 by 2 units, my E0 is changing 1 unit, right? Everybody following it? If I am changing this by 2 units, this is changing by 1 unit. And the sign will define, what does it define? If it is positive, if I am increasing this, this is also increasing. If I am decreasing this, this is also decreasing. If it is negative, dou E naught by dou W3. If it is negative, if I am increasing one, the other one is decreasing. And if I am decreasing one, the other one is increasing. So this will give me a sense of direction. This will give me a sense of magnitude on how much I have to change. So next I will do a W3 update of W3 plus dou E naught by dou W3. Why this plus here? Someone think about it?
Is that change?
That's a change. Because if you see, what you want E naught to go down. Right? So if the sign of this whole thing is positive, if W3 is decreased, dou E naught will also decrease. Right?
Right.
So if it is the opposite, if W3 is increased and dou E naught is decreasing, I will sum it to a negative quantity.
Negative.
So at the end of the day, when I add W3 plus dou E naught by dou W3, what will I get?
Negative.
Is it true? Or did I? Are you guys following? It's okay. If you guys are not following, we can discuss that.
No, but what, like you considering dou E naught by dou W3 as 1 by 2 right now?
Say it is 1 by 2.
Say it is 1 by 2.
Should I add that 1 by 2 to W3 or should I subtract it? Why add, why subtract? If I am adding it, why should I add it? If I am subtracting it, why should I subtract it? What does that mean?
So we need to understand what the value of is the error sorry.
Increasing or decreasing?
Yeah, error increasing or decreasing is fine. Whether your E naught and O1, right? Whether their difference is positive or negative. Based on that, you can decide.
So finally, what we are finding is the relation between E naught and W.
Right.
Right, irrespective of what is happening here, this will give me the dynamics of how my E naught will change with W3.
Right.
How my E naught will change with W3. What will happen if E naught increases? If it is a positive quantity, if this quantity that I get is positive, which value which is positive, if E naught is increasing, W3 is also increasing.
Correct.
Which means that whatever value I got, I should subtract it from the original one. Because if my W3 is decreasing,
right,
my total W3 is decreasing by a quantity of dou E naught by dou W3.
Right.
As this is positive, I am decreasing W3, which means that this is decreasing and E naught is also decreasing. So my total E naught will decrease when I decrease W3, if it is a positive quantity. So if it is a negative quantity, what will happen? It is the vice versa, right? So that negative into negative will become positive. So you are adding some value to W3, which means you are increasing W3. As its sign is negative, it will decrease. E naught will decrease. So your ultimate idea is to decrease it. So the sign should be negative. You have to subtract the difference. I tried to confuse you guys, just to make sure you guys are clear. You guys got this, right? समझ में आ गया? Clear. Just 10 more minutes and you guys will be among the 3% who understands backward. Okay. So now my whole idea is to identify dou E naught. It's pretty simple from here if you guys have come this far, right? Dou E naught by dou W3. So actually, if I break it down, this O1 was what all it had? 0.99. Okay, whatever. I have an error coming here. I have named it something. So yeah, I've named it out of O1. This is O1, right?
Right.
Out of O1, this is my input of
O1.
O1 that is coming. I just named it as net O1. Cool. And name it as net O1. Yes, net O1. And this is the weight W3. So this is exactly what is happening. Some value is coming, getting multiplied by W3. Net O1. That net O1 will then be used by the rectified linear unit, the ReLU function. That will give me the out O1. There could be other functions also. Here rectified linear output is just sending positive value and not the negative values, right? There is one more function called a sigmoid function, which is defined as 1 by 1 plus e power minus input. So whatever net output that comes, it will go through this function 1 by 1 plus e to the power of minus net O1. That will be the out O1. That will go next. This is complicated for our maths, so I am not taking that. And this is the most simplest. So if you have to derive this thing, the derivative is hard, right? Mathematically, it is computationally intensive. But for ReLU, the derivative is simply 1 or 0. What is the derivative of ReLU? Let's look at the derivative of ReLU. We will be using it next. So my ReLU function, ReLU of x, let me say, is defined as x if x is greater than or equal to 0 and 0 for x less than 0. So my d by dx differential of ReLU of x is d by dx of x is 1 for x greater than or equal to 0 and 0 for x less than 0. Here I am teaching you guys something wrong. I'll tell you why. You guys can look at it later. It is out of scope of the book, but just for the curious, I'll just tell. So basically, you guys have seen the differentiability, right? Continuity in differentiation. If you look at the differentiation of x at 0 here, it is 0. What exactly different? Okay, fine.
No, it is coming out as 1.
Here
It
1
should
and
be
there 0, right?
Yeah.
It is not meeting. From right side it is 0, so right side it is 1, from left side it is 0, which means the limit does not exist for its differential.
Right.
So differentiation is not possible at 0. Why is it not possible? It's simple, right? For a curve, it is differentiable everywhere because you can find a tangent there. Basically, when you are differentiating, you are finding the, what are you finding? Tangent. But for this particular function, at this point it is an elbow, it's an inflection. Is there a tangent defined there? Uska tangent bata sakte kya? We can't. For every point here, that line itself is a tangent. For every point here, this itself is a tangent. That's why its slope is always 0 here and 1 there. But here, at this point, there is no tangent because it's a bend, right? Strictly speaking, it's a bend. If you talk in more crude way, it's a bend, and at a bend, you can't find the
Tangent.
It is not smooth. So the tangent doesn't exist. So what these people have done is they have defined that, let us say, for greater than 0 also, what is it? At 0, they have defined it as 1. Okay, at 0, did they define it as 1 or 0? Check. So there are two definitions. I don't know which one, the different modules are using different ones. So it's our definition. So they have defined it as give me 1 second. You guys following it, right? Yes, sir. Here, everyone. As far as I remember, they have defined it as 0. You said 0 and non-differential function by using the sign. Software implementation usefully was 0. Okay. So basically, what? So basically they have defined it as 0. Okay. So at 0, the value is 0. Post that it is 1. So I can change the definition to say less than or equal to. But strictly speaking, it doesn't matter because you will see later. It tries to solve it. So you guys understood the definition of this, right? I'll use it later. Just remember this. Okay. Now we have this, right? This is just this one exploded. Out O1, net O1 is the input. This is the weight W3. This is 0.99, right? Okay. So the math works out to be. Now we have to do it. Now there is no space. But when we do it, it will just get inscribed in the. हाथ तो नहीं should turn it on, kya? Huh? Does this get on?
Choose the color. It should have charging, I guess.
Is it? Are you sure?
Yes.
Looks like
Connect करके disconnect.
इरेजर ऑन किया हुआ है क्या?
Okay. Please refresh the browser.
Must have selected the eraser.
हाँ.
Awesome. See, that's why group is important.
Return. Now select.
Mac application से ये बहुत complicated है. Okay, so okay, final. 5 मिनट में खत्म करेंगे. If you miss this, वो चले जाएगा इसलिए. Fine, you guys are still here, till here, right? E naught out O1, net O1 is the input, W3. Okay, so now I am trying to define dou E naught by dou W 5. Right? आ रहा है क्या? That's good. Huh? Minor. Only if my teachers give me marks for that. W3. Sorry. So this is defined as dou E naught by
साई चेयर पे बैठ जाए.
dou out O1. नहीं, फिर से वहाँ जाना पड़ेगा मुझे इसलिए. Thank you. Someone's giving. Dou net O1 into दिख रहा है ना? समझ में आ रहा है? हाँ से. You guys, is it visible?
Can you read it
Zoom
again?
करना पड़ेगा. Sorry?
Can I read it again? What is it?
मतलब वही.
I got it. I understand your problem. ठीक है, अच्छे से लिख रहा हूँ मैं.
zoom कर देगा.
वहाँ पे हो जाएगा.
Control plus.
वो वहाँ नहीं होगा.
साइड में प्लस दिख रहा है. राइट साइड में टैब पे.
No, वो collaborative में प्लस नहीं है.
अच्छा.
I'll have to plus it here, I guess.
बहुत बढ़िया. सब दिख रहा है.
दिख रहा है? Awesome. So this is dou E naught by dou W3 that we wanted to find ultimately. We wanted to know the relation of how E changes with W3. This is equal to dou E naught by dou out O1, whatever, right? It is written here. Dou out O1 by dou net O1 by dou W. ये जाएगा. It is this guy.
वो लास्ट में W3 होना चाहिए ना.
W3. Someone's calling. Okay, so we saw that, right? Dou E naught by dou W3 is nothing but dou E naught by dou out O1. So what exactly am I doing? So dou E naught by chain rule, right? This is related on this. This is related on this. This is related to this. Dependency. Dou E naught by dou out O1 into dou out O1 by dou net O1 into dou net O1 by dou W3. So it's basically you're cancelling the change of this with this, change of this guy with this guy. You're getting the change of dou E naught by dou E3. That's how chain rule works. Sorted? यहाँ तक हो गया? So now, tricky part, right? So now, let's take each and every individual out. Let us see dou E naught by dou E naught by dou out O1, right? Let's say dou E naught by dou out O1. This is equal to, so basically dou by dou out O1 into E naught. What was my definition of E naught?
1 by 2
1 by 2 into.
vibrated.
So I'll get the 1 by 2 outside directly.
Yeah.
Constant 1 by 2 into y pred minus by
By
out
true.
whole square. So my y pred was
0.0015.
हाँ, let's get there. Let's not substitute the value. We are just these are अभी equations है solve करना है ना. So this is how was my target, or target was my y true minus y pred. What was my y pred? This, right? Okay, out O1 was my y pred. Out O1 whole square. So you guys got till here, right? Let's go a little bit up. So dou V naught by dou out O1 equals half of this. So if I solve this, what will I get? So my dou V naught by dou out O1 equals. So when I do this, d by dx of x square is 2 into x power 1. So that 2 will come, 2 gets cancelled. ये 2 और वो बाहर जो 2 है वो cancel हो गया. So that's why we define half into that square. That half is because of that. So that 2 got cancelled. So you will be left out with target or y true minus out O1 into d by d out of target minus O out. That will be minus
minus 1.
1. Clear? So my dou E naught by dou out O1 is equal to target. What was my target? 0.
0.99.
What was my output of that out O1? Output of O1 कितना आया था earlier?
0.0015.
Amazing. 0.0015 into minus
Yes, again.
true, right? This is minus 1. Okay, I did a calculation mistake. But yeah, anyways. O1 is equal to whatever this value turns out to be. क्या होगा?
0.96.
96,
Mm,
98, 85, something like that, right? Minus 0.98 होगा या 7 होगा?
8.
Because 15 would give you 0, 1, 8, 10, 0,
Correct.
right? Sure. So this is my dou E naught by dou out O1. I made a mistake there. Fine? Yeah, the clear है? That's it, simple. This is what that does up now. Back propagation slowly gets there. So now, if I go here,
Okay, make it smaller here. I don't see that. For your convenience.
oh yeah. So now we have found out dou E naught by dou out O1. That is the first one, right? In the, if you guys look at this here.
Sorry. I could do that here.
Battery.
Battery over.
No, it's still recording. Just a reminder.
Okay. We are done in here. So see, we found out the first term, right? Now we have to find out the second term. So let's find out the second term. What was the second term?
Dou out 1.
Dou
Out 1 by
Net over.
out 1 by dou net O1. That will be how much?
Down by down at 1.
So basically, what is it that is in? What is the relationship? So you have to find out the relationship between net O1 and out O1, right?
Right.
So net O1 and out O1, what is the relationship? How is it that is defined? So my ReLU of net O1 is nothing but out O1,
One.
right? Exactly. So we'll get there. So my ReLU function, after applying it on net O1, I get out O1. So out O1 is nothing but ReLU of net O1. So my dou out O1 by dou net O1 is actually nothing but dou by dou net O1 of ReLU of net O1. Following?
Yeah.
Dow by dow net O1 of relu of net O1. What was this? Dow by dow x of relu of x.
1 and
1 if it is positive,
positive.
else it is
0.
0. So here my my net O1 was,
Positive.
you guys remember it, right? Which value आया था कुछ? So what is my derivative there?
1.
So my dow out O1 by dow net O1 is 1. This is the second term. This is the first term. This is the second term. Now the last term, right? Fine. Now what was the last term that we had to find out? Dow
Down at O1
by dow W3. So what was my relationship between net O1 and W3?
0.0. Yes, sir.
Sum of, yeah. So whatever my H1 ka output was, right? So H1 ka output, what did I name it as? H1's output? Out of H1, right? So out of H1 into W3. Anything else is there? Nothing. Here, this is the most simple this, right? So either H1 का जो भी output आया, I'm multiplying with W3. That will be my net O1. That is the input, right? If I were to take a general perceptron, I would have had a plus B also, which would come here out of H1 into W3 plus B. But here, for brevity, we did not take that plus B. Here, you would have had that plus B also. But we don't have it now. Even if it is there, it won't contribute to the gradient, right? Because constant derivative is 0. So it won't contribute to the derivative. So that's why I took this example. Even if it is there or not there, it won't make much difference. So now this is so dow net O1 by dow W3 equals out of H1. What was out of H1? We calculated something?
0.015.
0.015. Amazing, yeah. How do you remember everything? Did you write it down? Nah, didn't. Neural nets are fast and very RAM बहुत ज़्यादा है. So what was W3?
0.01.
Oh sorry, I did not derivate, right? Okay, so this is not dow net O1 by dow W3. Okay, sorry. This was just net O1, right? Net O1 was equal to out H1 into W3. So dow net O1 by dow W3 is equal to dow by dow W3 of out H1 into W3. So now dow net O1 by dow W3 is equal to, this out H1 is some constant into W3. So d by dx of Ax is A. 0?
Constant.
Constant है ना? W3 अभी, this is a variable. We are finding out how it is changing. So dow net O1 by dow W3 is out H1, whose value was, as I said, 0.015. Cool. So this was my missing piece. Third one, right? So I had first, second, and third outputs. Yeah. So the first one was just. It's okay. Yeah, I'll just write it down. My first one was dow E naught by dow out to out 1. That is nothing but minus 0.9885 into 1. That was nothing but dow. What was it? Dow out 1. Dow out O1 by dow net O1 into the last one is dow net O1 by dow W3. That is 0.015. This is nothing but the total dow E0 by dow W3. The actual change of E0 with the change of W3 will be equal to this, whatever this product is. Let's not get into that, but you guys got the idea, right?
Yes.
With the simple calculations of how chain rule can help us out in order to find out dow E0 by dow W3. Now, as we discussed, what can we do? Now all we have to do is,
One thing, I think it is 0.015.
हाँ,
हाँ तो वहाँ पे 0.0015 होना चाहिए.
नहीं
नहीं, नहीं.
तो इनपुट होगा ना, उसका भी वैल्यू है.
नहीं, सही है.
015 उसके बाद वाला है.
no, what you said was correct. Right? So, if you multiply this, you get a negative number. And we have discussed earlier that the formula that we have discussed earlier was, what was it? So now new W3, that is now W3 new equals, क्या हो? W3 old minus dow E0, that is nothing but our loss, our error, by dow W3. So my W3 new equals, what is my W3 old? The one that I started with? 0.1. 0.1 minus, ये कितना हुआ value? Let us take it as a minus delta. Delta value बाद में calculate कर लेना. So W3 new is equals 0.1 plus whatever that value delta, right? So finally we have a new W3. इतना करना पड़ा एक W3 के लिए. Now imagine solving that 728 वाला problem with that many number of weights and biases. Not possible, right? For which we need. So you have seen that there is a pattern that we can see, right? Every perceptron is the same. This with respect to this, with respect to this, with respect to this is the same. The derivative of the ReLU is the same. So you can generalize it, right? You can write for loops in order to compute the gradients here. Simple. So that's what they have done. They have made a package called AutoGrad, which does auto gradient differentiations. There are multiple packages that people have created. So yeah, this is the gist of how you have to change just one value. So now you have W3, right? Now this you can change W1 and W2. It's just one more step. Let's do it. I don't want to do it. Right? Enough. But you guys got the gist of it. So I guess this is the last time we'll be doing calculations like this, because we'll see what exactly it is. So okay, let's इसको ऐसे अभी latent RAM में रखिए everyone. I'll just show you something and then we'll come back to this one a little. Okay, Jupyter installed.
Yes, it's already open. Open localhost. Check.
Oh, yeah.
The other one open localhost.
It is open.
Go localhost in the other one. It's open.
Perfect. Okay. So all that we have done so far, let us see how we can quickly. How we can quickly do this in like, how many steps are these?
Can you zoom that?
I'll do that. 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of this 10, most of it is boilerplate code. You just can do it in 10 steps. Done. Sorted, right? Okay, so more? Cool? दिख रहा है? और थोड़ा?
This is fine.
Everything comes. Cool. So let us see. You guys have done the assignments, right? Good students, good chaps. Fine. That's why you guys know, like, huh? क्या हुआ?
Rubel ने नहीं
Look
किया.
at me.
Well, assignments. So import keras, input numpy, you guys know what these are. Please, I suggest before we go into the next session, you guys try to finish those assignments so that these things are going to come now. It will be very interesting. I guess you guys are that bunch who are like interested into this stuff. You guys know what is going on. Like, it is doable by everyone, right? And you guys are sticking to it. That's the most important thing. You guys are sticking to it till the end. I'm pretty sure we'll do the face recognition one. Pretty sure. Like, that thing, that is, now you are in the top 3%. Clap for yourself, please. Please. Seriously, nobody knows back propagation. I'm not even...
The bottom 3% of the top 3%.
That's nice. Okay, so import Keras, import NumPy, these are two libraries that we are importing. You guys have at least heard of Keras, right? Keras. Kira. So you guys have to actually do that assignments, right? Good. So Keras is one of those high-level libraries where all these abstractions, right? Like perceptron, and you are going to look at convolutions. There is another form of perceptron, but at a different. It has a different rationale. So all these things, they have been abstracted and put in a library called Keras. 1, 2, 3, 4, 5 letters and like done. All these things that you have learned so far can be done in these 10 lines. So import NumPy as NumPy. You guys know what NumPy is, right? NumPy is what is NumPy? Array manipulation library, right? With lots of functions like linear algebra and everything. So what we have done so far is just one dimension, right? If I take multiple examples, this thing has to be done in a different way. What we do, we put matrices, right? Same operation that I do on one thing, A plus B, A into B plus C, I can do it in matrix 1 into matrix 2 plus matrix 3. That's it. So NumPy is used for that. So all these things is something which is relevant right now. It is a sequential model or a model. It is a model that I am creating, right? I am importing from Keras models, those models, and layers. I am inputting something called dense and input. Input is this guy. Input. And that dense is this layer. And this layer is the dense layer. This is also dense layer. This is also dense layer. So the perceptron that we are talking about, if it has multiple layers, it's called a multi-layer perceptron. And these guys, because they are competing with other frameworks, they have named it as dense. Everybody is following that. It's called a dense layer or a dense network that we are creating. So I'm importing from Keras' layers the dense. That is these layers. But I have to take the input somewhere, right? I have to hold the input somewhere. So I have got an input wala layer. So I am defining that input, that variable input INP as input of the shape to be 2 and nothing. So it has two inputs, right? 0.05 and 0.10. So I am just telling, be ready. I am sending you a 2, 2 values. Yes, 2 values. So I am specifying this is the shape, this is the input layer that I have imported, and I have named it as INP. H1, right? You guys know H1. What is H1? Hidden layer, exactly. So this is the hidden layer. It has a 1 per perceptron, right? 1 node. Only 1 node, right? I told you guys already, right? I can have multiple nodes here. I could have as well defined it as 10 here. And this Keras would do all the calculations and all the connections on its own. How we are connecting them, we'll see next, right? So this is H1 equals dense, 1 node, activation?
Activation function.
ReLU. We have discussed. Here instead of ReLU, if I change it to sigmoid, it will change it to sigmoid. And it does all the calculations on its own. That's there. Activation ReLU. Use bias, false. Because ज़्यादा नहीं करना है, आज कम करते हैं. So false. Kernel initializer, Glorot uniform. I used some function that they have which initializes kernels. Not from zeros but with some values. We have initialized 0.1, 0.1, 0.1, right? I can do that. I can manually also initialize some values. But these guys have given a function which they say is good at initializing values. This is all some Glorot uniform. It's just like some uniform distributed kernel. So that's how I am initializing random. So this H1 I am connecting it to input, that input. So this is just that convention. This is that OOP convention. So I am connecting this input to H1. Done. Next line I am out is the output. It is also a dense perceptron with how many nodes in it? One node. Activation, bias, kernel connected to H1. So now this is connected to this is connected to this. Whatever this out value, whatever this variable out has, the value, that is nothing but this. Cool? Done. Warnings, all that. Now, that is there. I just have defined my architecture. But now I have to define what the model is, right? I can define my model only from here till here also, right? I can say output is this, inputs are these, define a model. So my model is only from here till here. But for us, whatever problem we have solved, this is the output. This is a model. So I will define these as the inputs, these as the output, this whole thing as the model. So model equals model of inputs are INP, the input, and output is OUT. Right? I just gave that list. This model.summary is a helper function that these guys have written, where if I do whatever model I have defined, if I do model.summary, it will give me a summary of the whole model. It will give me a textual output of what the model would be. So how many parameters do we have right now here, which we are learning?
3.
3? You sure?
Output.
Learnable layers. Kitne? 3. Right? W1, W2 and W3. So, magic. Your hands? 3. Trainable? 3. If it were bias? 5. Because we will have
2 and
here 1 and here 1. We can have here also. Then it will become 1, 2, 3, 4. 4 more. So 7. Something of that sort, right? Total number? 3. Perfect, right? All our math is working out.
Plot model.
Okay, is that available?
Keras.utils.plot model. One more second. Just add one more. Keras.utils. No, you already imported Keras. Utils. PLT. Model. Model. Only model.
Inline it is not plotting, no?
It's not model.
Why is it saving? Okay, it is outputting something. Okay, I'll save it as file. Hmm?
It does show it.
It has to file.
Platform name dot page.
They'll not PNG.
In string.
No worries, your model.png. You guys can see? This is the input layer. This is the first dense. That is the hidden one. Yeah. You go zoom in. Input layer, dense, and the output dense layer. Right? This is just the model. So if you have multiple ones here, it will go like this and come. It's just for visualization purposes.
Escape.
Okay, cool, that is done. So now I am defining my x and y. X is the input, y is the output variable. X is the input variable, np.area of 0.05, 0.05, 0.10, 0.10, and y is np of area of 0.99. So provided these two inputs, my model has to learn to output 0.99. right? Here what I am doing is expand dims. It will expand the dimension to 1. It will expand one more dimension. Why? Because usually I told you, right, we'll mostly input to the model batches. We can't input all the images at the same time, all the examples at the same time. So we break it down into batches. So it is usually like this. So if you are sending X and Y, you will send batch, comma X and batch, comma Y. So 10 examples of X. If it is 10 examples of X, here the batch will have one more dimension, right? That is, if X is a single number, if there are 10, you'll have 10 of those X's, right? So there will be 1 comma 2 will be the, that's it. I'm just expanding it to the, if you look at the shape of it, earlier it was only 2 values going in, right? Now it is 1 comma 2, because that extra dimension is nothing but the batch wala dimension, right? You guys got it? Y shape was just a value 1, but it will become 1 comma 1 because the extra dimension is the batch. Here batch may we have only 1, but Keras in general takes batch as an input. So even if it is one example, you can't directly feed one example. You have to batchify it into a batch of 1, which makes no sense, but that's how it takes in. Now I compile the model because I have to use some optimizer. You guys remember SGD, right? Gradient descent, all the fancy stuff that we have seen. And the loss, what is MSC? Mean squared error. So I'm compiling my model. I'm telling this model that I have defined, use optimizer as SGD and loss as mean squared error, self-explanatory. I'm just saying now, model.fit is where my fit happens. Let's run it for 1 epochs. An epoch is defined as?
Some time.
Yes. In general, epoch is time, right? In general sense. But here in our context, epoch is, 1 epoch is defined as the iteration in which all the points, all the data points in our data set have been passed through the model once for training. All the data points. Right now, we have only 1 data point. So 1 data point going through our model once is an epoch. I'm just running it for 1 epoch, right? It's done. It took just 287 milliseconds to do all these calculations, right? And your loss is 0.9801, right? You have gotten your loss. Let us see what is the predicted model. So I am model.predict. It predicts the value, right? Which means I input my X, it gives an Y, that is the prediction. Predict, print of predict, it predicted 0. I know what it happened. Let's see. It's constant. That is the problem with ReLU. So, just give me a second. Okay, we'll do one.
What was the problem there?
So it has a diminishing gradient problem. So if your weights are initialized as 0 and 0, you're always your gradient will be at 0, which means you're not learning any weights.
Okay.
In the first 1 into 2 into 3, the 2 will
Right.
always be 0. So once it is 0, it is whole thing is 0. The
Zero,
weights
right.
are the same,
Right.
which means it will contribute to the same 0 gradient time area. So
Okay.
which means it is getting stuck at that local minimum. That's a problem. It's okay. We can solve it with bias, but I did not want to show an example with bias. Right? Awesome. So initially the loss was 0.990, then it got down to 0.989, right? It is not showing. There are, if you go to other significant digits next, it is actually decreasing but very minuscule value, right? So this is happening slowly, this is changing, and your prediction after 10 epochs is this much. Let us see how much more we can do. Let's do 10 more. It's the same. Okay, this is also going to local minimum or what?
No, you haven't changed
This is
the.
getting reduced. It is.
But did I not print this?
No, box is all.
Right? It's slowly changing.
Make it 10,000.
Mm.
Click on
बस scroll करने में problem हो गई.
hide that this thing out. Hide the key.
Oh man, this local CPU में चल रहा है. हट जाएगा.
Better. 5 minutes.
आने में बैठ जाओ. टिपिकल के आ जाओ. Your model will be ready with your session. So you guys can see, right? Slowly the model earlier was 0.9. It's decreasing, right? The loss is decreasing. I can stop it even now. Let us see. Model will predict 0.88. Slowly getting to 0.99. So here we know that this dense network is not very apt for this solution, and without bias also it is very hard for it to generalize. But you can see it is slowly moving towards 0.99. But if you have multiple data points for which this had to generalize, it had to fit, your X will only increase. Here instead of giving this, you will give an np.array of multiple arrays like this. A stack of those arrays, this will have a stack of those predicted values, outputs, and you will define your batch. So say you have 10,000 and 10,000 examples, you can batchify it of 100 and 100. And one epoch will have how many number of iterations? 10,000 है, 100 का एक batch है. कितने होंगे? 100. So 100 steps. So here this thing is there, right? This. Here it is 1 of 1. There will be 100. So 100 of 100 खत्म होने पे one epoch gets over. Sorry, right? And however many number of epochs are there, it will show what is the epoch number and that many epochs. And this will generalize to both of them. You are getting the hang of it, right? How this is being solved. So
What are the weights?
you can see them, but I should have actually put that also. You have to visualize weights, right?
Model.weights.
Model weights are giving everything. This will go into visualization.
Not visualization.
डिम्पल बोले कल ऑफिस आएगी तो बता दे.
These are the weights. This is for which one? Which layer?
I think it is last year's.
It's only last layer, right? Because it is printing. Should have printed there. Those are the weights. These are the first two. This is the other. 4.08, 1144. You can check it out also by going this into that plus this into that plus that. I'll have to give you that. Right. Always, right? It is, let us look at it. 0.1 into 0.05 into that plus this. This into that. Okay. I'll have to do the math. Cool. You guys got it, right? So these are the weights. You can print the weights and look at it. Just quickly look at ReLU once again. I want to see it with ReLU because ReLU ReLU reaches the solution faster. In 10,000 it actually reaches to 0.98. So I want to see that once. Okay.
Total for 100. Is coming 0.
Coming 0. That guy is taking 0 now. Blur uniform change कर दे.
Try normal.
And remove the kernel initializer.
By default it is this.
Hmm?
By default it's this.
Yeah, right.
You put normal. Shift tab.
Kernel initializer, kernel read matrix, C initializers dot.
Just try normal, right?
Normal distribution, huh? It's normal, right? Okay, cool.
The name is wrong. Name might be wrong.
Keras. Start with one, sir.
Go up, go up. The random info.
Oh. Sometimes cache problem. Sorry, what?
No, if it's 0, don't know.
If it is 0 initially,
It's not about initializing problem.
that also helps. So you can see that loss is going down, right? 0.4, 0.3, 0.35, so on. If you predict and print the prediction, it is 0.39 right now, right? And if you change it to say 1000, yeah. So earlier it was 0.39, right? 0.98. Okay, we have reached. We have reached the end of the session also. Let us see how much more can it do. One more 1000 run करते हैं. 0. कितना था value? 998? 986314006, right? 986314006. 0.9899773. 9899 is close enough to 0.99, right? I guess. Done. And when the weights have been updated, you can see. Weights have been updated. Yes, we can't do. Okay. Wow. One of the most complicated sessions is done. So let's see what we can do in the next session. Anything? Any doubts in the session? Anything you guys want to add? Nothing.